Okay, so of course usage of De Moivre's theorem is just not limited to simple things like this. Okay, there's wider implication or wider usage to your De Moivre's theorem. So what happens is, I'm going to show you an example, minus half plus root 3 over 2i. If I raise you to the power of 3, activate De Moivre's theorem, I get actually 1. Similarly, for the complex number negative half, minus root 3 over 2i raised to the power of 3, I also get 1. So what it means is that for the roots of z cubed equals to 1, the roots are basically 1, negative half plus root 3 over 2i, and this. Okay, so with the knowledge or understanding of De Moivre's theorem, we actually can solve for things like what we call roots of unity. Okay, so the fundamental theory behind roots of unity is your trigo concept. The idea that you are allowed to add 2 pi or subtract 2 pi or add 4 pi, add even number of pi to your answer. So if this is theta, this is theta, it is actually equivalent to theta plus 2 pi. Is equivalent to theta plus 4 pi. Is actually equivalent to theta minus 2 pi. So in general form, it is equivalent to theta plus 2k pi, where k can be any integer, be it positive or negative. Okay, so this is your concept on the cycles in your trigo. So with this, what I can do is, for z cubed equals to 1, I'm going to change 1 into REI theta form, or your exponential form. So if 1, the modulus of 1 is just 1, the argument of 1 is actually theta, is actually 0. 0 is the same or equivalent to 0 plus 2k pi. So z cubed is going to be equals to EI 2k pi. Then based on the rules of indices, z is equivalent to 2k over 3 pi I. Okay, then if I choose, I let k be equals to minus 1, 0 and 1, I will actually get 3 answers coming out from there. And these are the 3 answers. And these 3 answers are actually equivalent to these 3 answers that we have previously. Okay, so the important rule is that I need to use 3 consecutive values of k. So what happens if I use other values? So instead of using minus 1, 0, 1, I use minus 3, 2, minus 1. I can actually add up or generate all the different solutions coming out from this. Okay, and then you actually realize that the things happens in cycles again. This one is the same as this one. Okay, 2 pi over 3 is equivalent to 2 pi over 3. Okay, it's equivalent to here. And then you have your negative 2 pi over 3 equivalent to this and this. Okay, so things happens in cycles of 3. So in general, okay, you need to choose 3 consecutive cycles, or 3 consecutive numbers. So another example 4 to run you through. I want you to find the 5 roots of this equation. So change 32 into REI theta. Modulus of 32 is 32, argument is 0. So z5 is equivalent to 32 EI0. Then, based on the concept of adding cycles, is equivalent to 0 plus 2k pi. Okay, so z taking 1/5 on both sides is equivalent to 32 1/5, EI 2k pi, and then use 3, or rather in this case 5 consecutive k values. Okay, you can use anything. Okay, and then you will generate these 5 answers. So the question now is, why do I specially choose 0 and plus minus 1 and plus minus 2? Why don't I just use 0, 1, 2, 3, 4, 5? Okay, so the simple rule is, I keep the number as close as possible to 0. So when I say keep it as close as much to 0 as possible, it means that to the left and to the right, so that your argument that come out from them, okay, actually is already in the acceptable range for your argument. Okay, so take note again. Okay, let's reverse back. This is actually a power 5 equation. Okay, if I look at it on another way, it looks like that. This is a power 5 equation with real coefficients. So your roots should occur in conjugate pair, and you should realize that these and these are actually conjugate pair. These and this is actually a pair. So actually you have two pairs of conjugate root, okay? Two pairs complex root and one real root, which is consistent with what you have learned in your chapter 1.